continue on here, chapter 19, I think. So really in this chapter, last time we were talking about coordination, compounds, and complex ions. So remember that a coordination compound, you can really think of it as sort of as a ionic sort of compound. There is a positive ion and there's a negative ion. And it's really made up of two parts. It is made up of the complex ion, which has obviously a lot of times transition metal in the center, a bunch of ligands attached to it, and also a counter ion. And really the counter ion is there to balance out the charge, like in a sort of normal ionic compound, to sort of equal zero in terms of the overall charge. Now you can have both the counter ion and the complex ion. They could either be positive or negative. So for example, we can have a counter ion that is positive. That would make our complex ion part negative, and vice versa as well. We could actually lead with the complex ion, which will be positive, and the counter ion will be negative. So you can have both, obviously, a positive or negative complex ion and a positive or negative counter ion. Now, when we name these, when we write the formulas for these, it is just like an ionic compound. It is always the positive guy first, followed by the negative guy. So again, both in the formula and also in the actual naming, excuse me, process as well. We also talked about the idea of sort of naming these guys, and it does depend on whether or not your sort of complex ion is positive or negative as to sort of the approach. A lot of times when you do write the formulas, you will find your complex ion in brackets. And if your complex ion is positive, then we use sort of the regular metal name, and that always comes at the end of the complex ion part of the name, along with a Roman numeral to indicate the charge on the metal. We also will name the ligands that are attached in alphabetical order. And remember, some of the ligands have some special names as well, but we do put the ligands in alphabetical order. And that is regardless of prefix. So again, if you did have, say, a couple chlorines, for example, it would be dichloral. So we would look at just the C part of the name rather than the D for the di. Now, if your complex ion is negative, it still works pretty much the same way. You're going to go with your ligands in alpha order as well. But the metal will be really kind of maybe like the old school way of naming metals that typically end in 8. So like ferrate, cuprate, plumate, zincate. So depending on the metal, we still will use Roman numerals as well to indicate the charge. As we also talked about, again, even on things that we normally maybe would not put Roman numerals on, we still will use sort of Roman numerals here in sort of naming these guys. In addition, even things sometimes with a 0 sort of charge, so you have like a neutral metal, you'll put a 0 sort of where the Roman numeral will go. Then obviously the counter ion is named just like you normally would. It really, in most cases, doesn't matter how many of the counter ions you have. You pretty much just use the name of it. So if it's a positive counter ion like a metal, like potassium, you would just call it potassium, even if you had 2 of them or anything like that. If you had maybe like a negative counter ion, like nitrate that we saw earlier, you just sort of use the name, or if it was Br2, bromide, so you just sort of use the normal names for those guys as well. We also talked about coordination number. Coordination number really, again, is the number of atoms that are directly attached to the central metal in the complex ion. And it's really important to understand about the ligands in that situation. Ligands being Lewis bases, which means that they can donate a pair of electrons. Some ligands are monodentate, which means they basically attach in one place per sort of ligand. Some are bidentate, which means they can attach in, say, two places per ligand. And there are some polydentate ones, which, like we saw, I think EDTA can actually attach in 6 different places per one molecule. So that does make a difference when you look at your metal ion that's in the center. You know, if you have a monodentate like chlorine attached, the coordination number in this example would be 4, since obviously only one atom is being directly attached to the metal in the middle. If you have a metal where maybe it is something like, say, oxalate that we talked about, I think, as well. Maybe got just a couple of these oxalates happening. Each oxalate can pretty much bind into the metal through the single bonded oxygen, and the coordination number, again, in this particular case would be 1 atom, 2, 3, and 4. So the coordination number here would be 4. And again, sometimes people get into the habit of like looking at like the formula and it goes like, okay, so that's 4, so that's the coordination number, as opposed to if you had a metal and like our oxalate here, you would say perhaps 2, but again, because it can attach in 2 different places per molecule, the coordination number actually is, again, 4 here. Any questions on any of that stuff we talked about last time? All right, so where we left off, I think, is here. We're going to talk a little bit about isomers. For the most part, isomers are things that have really the same molecular formula, but oftentimes it does have some different connectivity. So although they may, say, for example, all contain, say, 4 carbons, 8 hydrogens, and an oxygen, the way all those atoms are arranged are typically different. And what that usually will give rise is to 2 different types of compounds that have some distinct properties from each other because they are sort of arranged differently. So there are really a couple of different sort of classes of isomers we're going to talk about. There are structural isomers, which have different bonds. And underneath that, there's really 2 types of structural isomers. That is coordination isomers or linkage isomers. The other type ones are referred to as stereoisomers. They say have the same bonds, but really sort of different spatial arrangements. So although they really do have everything sort of connected up the same way, the bonds are arranged differently in sort of 3-dimensional space. So that gives rise to 2 types of stereoisomers, one known as geometric, which gives rise to cis or trans isomers, or optical isomers, which has the ability to move plane polarized light. So let's take a look at some of these different types of isomers. So here, if we just really count up everybody that's involved in both of these coordination compounds, we pretty much got the same of everything. We got 1 chromium, we got 5 of the NH3s, we got 1 bromine, and we got 1 sulfate. So they really are made up of really all the same elements. But these type of guys here are different in the way that the elements are attached. For example, we know that in this particular case, right about there is our complex ion, which means if we kind of roughly just sketch the complex ion, we have a chromium in the middle, We have basically 5 of these NH3s attached. I won't draw them all out. One, two, three, four, 5. And we also have a sulfate that is attached here. And this overall complex ion has a +1 charge. In this case, it is the bromide that is acting as the counter ion. So in the first example, the bromide is not directly attached to the metal. It's not really acting as a ligand in this particular case. It is basically acting as the counter ion to balance out the overall charge. And that's different than what we see down here. Down here, when we look at our complex ion part, we once again have the chromium in the middle. We got our 5 NH3s. 2, 3, 4, and 5. But in this case, though, the bromine actually is directly attached to the complex ion, and part of the complex ion in this part, this is going to give us a +2 overall charge. And here it is actually the sulfate that's going to act as our counter ion in this particular case. So these guys are referred to as coordination isomers. They definitely have the same number of each elements present, but again, the connectivity is different. And obviously, because the top guy and the bottom guy actually has some different ligands attached, it will probably also have some different properties. And it also, as you can see, gives the complex ion part a different charge as well. And that overall different charge is also going to have some effect on some of the properties that you would see for each of these guys. So one type of isomer is a coordination isomer, where we may have a certain element that's being a counter ion in one case, but actually part of the really kind of working part of it, which is the complex ion part. Any questions on that there? All right. Another type of isomer that falls under sort of structural isomers is what's known as a linkage isomer. And in this particular case, it's actually the sort of same ligand that's attached there. The difference, though, comes from how it actually links into the complex ion. So NO2, it can actually link in through both the nitrogen part and the oxygen part on it. It will not do both of them together like a bidentate, but it does have the ability in certain cases for the nitrogen actually to get in there and sort of attach to the complex ion. And in other cases, it's the oxygen that will do that. So again, on the nitrogen here, there is that lone pair that allows it to donate it like a Lewis base. And obviously on the oxygen, we got some lone pairs that would also allow the oxygen to do so. So in the case of the top sort of isomer, the connection is actually happening here through the nitrogen on the NO2 minus, as opposed to in the bottom one here, the connection to the complex ion is actually happening through the oxygen part of it. Again, they're both the same ligand. They're both the NO2 minus ligand, but it does actually have a couple kind of polar elements on there, and they also have some non-bonding electron pairs. So that gives both of them the opportunity to sort of bind in. But again, they're not going to sort of do it together in this case. One or the other will sort of get in there and make that bond that will happen. Any questions on that there? All right. So let's talk then about sort of the other classes of isomers, which are stereoisomers. Geometric isomers like cis or trans. So typically you see a lot of cis or trans in organic chemistry. Cis means that it's the same side, and trans means that it is opposite sides. And in sort of basic organic chemistry, what you're talking about is really a lot of times the double bond. So either you got like a group on the same side, which would be cis, or you got a group on opposite sides of the double bond, which would be trans. So And a lot of isomers that we talk about here, we will have either groups sort of on the same plane, if you will, of the molecule, or on opposite sort of planes of the molecule. So these are guys with the same atoms, the same bonds, but will have different bond angles because of their arrangement in sort of three-dimensional places. They're common in square planar complexes. Square planar, as you may remember, is an expanded octet. Yes, we got like a square and some non-bonding electrons all within a plane where they come together, basically. Kind of 6 electron pairs and 4 bonds, basically, is what you got going on there. So that's what we see here. So within this plane, the top one is the cis isomer. We can look at our NH3 groups. They're basically on the same side of the plane. And also you can even look at the chlorine groups as well. They're also on the same side of the plane. When we look at the trans one, we have our sort of guys on opposite sides of the plane. Same thing with the chlorine, if you want to look at the chlorines as well. And again, it gives this guy some different properties. They are all sort of still attached really the same way. They all have the same bonds. They all have basically our platinum to chlorine bond and our platinum to nitrogen bond in the case of the NH3. But again, just sort of their arrangement in three-dimensional space is a little bit different. Now, these are also some trans isomers and cis isomers in sort of a coordination number of 6. So this was a coordination number of 6. As we can see, 4 and 2 gives us 6. And that's different than here, where we're looking at a coordination number of sort of 4 here. Now, in this particular case, we sort of have, if you want to think about it, the plane of the molecule sort of happening, where this part is. And in this particular case, what we have on the left there is our trans isomer, and we could look at the chlorines. We sort of have a chlorine above the plane of the molecule. And we also have a chlorine kind of below the plane of the molecule. So you can think of that plane as sort of a separating point, and they're both opposites of each other for sure. On the right, we have basically our chlorines on the same side of the plane. They're both sort of above the plane there. And that would be a cis isomer in this particular case. Now, optical isomers are isomers that have the opposite effect on plane polarized light. There are a couple of terminology that we use for stereoisomers and these type of isomers. One is what's referred to as being chiral. So if it is a chiral isomer, it means that the mirror image, as it says there, is non-superimposable. So as we'll see a picture in just a second, what that means is if you put your left hand up to the mirror, you get your right hand staring at you. And basically, if you take out the mirror image, which would be like your right hand staring at you, what it means is you could do whatever you like to that mirror image, rotate it, move it around, but you'll never get it to line up perfectly with the original sort of structure, if you will. And if you do that with your hands, you can move it around as much as you want. You can get the thumbs on the right side, but palms up, palms down doesn't work correctly. You get palms down and palms down, but thumbs are now on the wrong side. So in terms of things that are chiral, if you take the mirror image out, and even with rotation and movement around, there's always going to be something that is sort of in the wrong location. So there's something that's out of sorts and will not allow the mirror image to sort of superimpose on it. Something known as achiral, which you sometimes also hear about, that is when you actually do have something where the mirror image will superimpose. So if you do take that mirror image out, you can, with maybe some rotation, get it to fit perfectly on the original structure. And that's sometimes referred to as an achiral compound as opposed to a chiral compound. So plane polarized light, as you go through it here, it basically separates out the light through the filter. and it kind of has it in both directions. You could also measure, if you put a sample in there, the angle at which it's able to sort of move the plane polarized light. We're not going to get into that much of that. But there's our mirror example with our hands. And again, palm up and palm down. So again, they do not match, even though the thumbs are on the correct side of the hands. So if we take a look at some of these mirror images of some compounds here, isomer 1 and isomer 2 here are mirror images. And the image of 1 is identical to the image of 2 here. So if we, and they cannot be superimposed basically. And it may be really hard to sort of see here, but the difference comes in sort of the reflection. So this nitrogen gets reflected here. This back nitrogen actually gets reflected back there. But is the connection between these two nitrogens that's actually different. In the original image, it is right here up in front. Because of the reflection that happens, if we pull out the mirror image, that connection is now to the guy in the back. So what that means is every time you would sort of rotate this guy here on the right, there will definitely be a bond that's sort of out of place, and there'd be non-superimposable on each other. Now, if we look at the trans isomer here for this particular guy, and we do the reflection, this guy, if we pulled out the reflection, will actually superimpose on each other. We basically got the same bonds happening here and here, here and here, and then obviously through the middle there, they're all the exact same bonds. So in connection, so they will superimpose. Once again, though, if we look at the cis isomer as it reflects, we have our chlorine that reflects here. We have our back nitrogen that will reflect to the back. And again, because of that bond between those nitrogens have now become this bond back here. Again, we now have a different connection when we pull out our isomer image. And that difference in that connection is going to allow them not to really be superimposable on each other. So those guys that are not superimposable are basically a pair of what are referred to as optical isomers. They'll be able to move sort of that plane polarized light. So two molecules that have mirror images that again are non-superimposable are what are referred to also as being enantiomers. A lot of biomolecules are chiral, and a lot of drugs are as well. So sometimes one isomer, depending on the connectivity, can actually do some good things, and the other one is sort of a dud, just based on this sort of differences in the connectivity. Any question on isomers? All right, so to finish up on this chapter here, we're going to talk about sort of what happens with the electrons in the sort of complex ion and really the transition metal, sort of how the electrons get distributed in the presence and in the absence of certain ligands. So to help us with that, the formation of hybrid orbitals to share electrons. If you remember hybrid orbitals, that's like your sp, sp2, sp3, sp3d, right? sp3d2. These go with certain geometries, right? Electron pair geometries. That's like a linear, right? That is a trigonal planar. That is a tetrahedral. That is a triangular bipyramidal. And that is your octahedral sort of arrangement. Vesper model works well for regular things, but it doesn't work so well for complex ions. So as I mentioned sort of earlier, we think really more of complex ions as sort of an acid-base sort of situation, and more specifically, the Lewis acid-base sort of interaction that's happening. Hybrid orbitals used by metals does depend on the number of ligands that are present. So again, here are NH3 bonding in In this case, we have 1, 2, 3, 4, 5, 6, coordination number of 6 would give sp3d2 arrangement, which would be octahedral. By the way, to assign hybridization, the really simple way to assign hybridization is this. And you basically count up electron pairs like you do in geometry. Double bonds, triple bonds count as just one. And basically, if it had, say, 4 electron pairs, you could just count this off. And that would be 4. So that's an S and basically 3 Ps. If it had 2 electron pairs, you would just take 2 of them there, and that would give you your sp hybridization. Now, the certain geometries that we see that do go with certain coordination numbers, these are very common ones. This is our tetrahedral geometry that we see with a coordination number of 4. We also do see that square planar with a coordination number of 4, and our linear sort of geometry is typically what we see with a coordination number of 2, basically, that's happening here. And again, this is sort of the 3-dimensional arrangement of those guys as the ligands come into our metal. Again, the ligands donating the electrons, the metal being electron deficient. So let's talk about our d electrons, which is typically the electrons associated with transition metals. As the transition metals, as we talked about at the beginning, that is our D block, right? Our transition metals. Our D block on the periodic table. And basically there are 5 different d orbitals, and here they are. We got our z squared, x squared, y squared, xy, yz, and zx. So these are the 5 different d orbitals. Now, if we have a transition metal without a ligand, what we will see is all 5 of those d orbitals will basically be exactly the same in terms of the energy. So each of those orbitals will basically maintain the exact same energy. And that's important for how electrons will fill these orbitals in general, right? Electrons fill orbitals 2 at a time, 1 at a time. They fill them 1 at a time, right? Until they all have 1 going in sort of the spin quantum number plus a half, right? And then they come back and pair up afterwards, going the other way. That's what's known as Hundrel, right? Maximum parallel spin is what we're trying to achieve. And then we come back and pair everybody up. So in the absence of any ligand, we would expect our electrons to sort of populate the d orbitals like they normally do. But when we start to get some ligands that are attached, there's actually some separation that actually occurs between the different d orbitals. So, and that's what we see here. So in the absence of our ligand, our d orbitals are perfect in energy. And when we do start to get some ligands attached, there's actually a separation of the 5 different d orbitals. So in this particular case, this is an example of a coordination number of 6, which is an octahedral sort of geometry. And what happens in that is we get the xy, yz, and xz orbitals to actually go lower in energy. By all of our squared guys here, x squared, y squared, and z squared orbitals actually go higher in energy. Now, the difference in the energy between the sort of lower d orbitals and the higher d orbitals, this difference in energy is what is referred to as the crystal field splitting energy. It is sometimes abbreviated with a delta symbol there, or it may even be the energy sort of symbol is used for it. And that is the difference between 2 sets of d orbitals in a metal atom when a ligand is attached. So This is important because of how the electrons will populate these d orbitals depending on which ligands attach. So the two sort of scenarios that can happen in this situation is we start to sort of populate our electrons. And let's just say, for example, we had 4d electrons to sort of populate into these orbitals. What's going to happen in this case is, like normal, electrons always fill from the lowest energy to the highest energy. So we would start to populate our lower orbitals, d orbitals, first with our electrons. And it's at this point when we get to, say, our fourth electron, we have basically a choice to make-ish. And the choice is based on this crystal field splitting. If the difference in energy between the lower d orbitals and the higher d orbitals is not all that much, we would expect that the electrons would basically start to populate like normal, and the next electron would go to the kind of higher energy level there. Now, if we get to that situation and we analyze the crystal field splitting there, and it is considered, a relatively good distance, if you will, what's going to happen is the electron's going to decide, I do not want to go up there. That's like way too much energy. I would rather come back through here and actually populate the lower energy guys first and start pairing up. So in certain situations, based on sort of the difference in the energy between the lower and the higher d orbitals, you will get electrons that will populate like normal, one at a time, until they run out of space and then come back and fill up. Or you may actually get some that will actually start pairing up before they fill up all the d orbitals, because it is such an energy difference between the lower ones and the higher d orbitals. Any questions on that there? So if we look at this, we could actually calculate a couple of things here. We could calculate the crystal field splitting by using this equation that you might remember from Chem 50. That is, the energy is equal to H. H is our Planck's constant, 6.63 times 10 to the minus 34 joules times seconds. The little nu there is actually the velocity, right? That's not the velocity, that's the frequency. So that is the frequency. Frequency is typically given in reciprocal seconds or a hertz, right? A hertz is the same thing as a reciprocal second. So those two guys are basically equal to each other. This also really does go back to a couple of other equations that maybe you remember as well, and that is C is equal to the wavelength times the frequency. Wavelength here being in meters, frequency being in 1/seconds, gives us the speed of light in meters per second. C is equal to 3 times 10 to the 8 meters per second, which is a constant. And putting both of these equations together, you also can solve for the frequency, which would be the speed of light divided by the wavelength. And by the way, the wavelength would be the speed of light divided by the frequency. And you can stick it into that equation and get E is equal to H times the frequency, or E is equal to HC divided by the wavelength. So that allows you to calculate the energy difference, for example, if you just know the wavelength of light that's coming off or has been absorbed by a system. Any question on those equations? When we do measure absorbance values, for example, like we've done in a couple of experiments, we always want to select the wavelength of maximum absorbance. So a lot of times what you would do is you would take a sample, maybe your most concentrated sample, for example, and you would measure its absorbance value at different wavelengths. And you would want to pick the maximum wavelength here when you do these type of experiments. And when we use our sort of samples in lab, the computer sort of selects it for you. That's that really colorful graph at the very beginning where it auto selects like a wavelength, right, on the little curve that goes like that. And the reason we would want to do that is if we take the wavelength here and set our system to that, we should be in good shape when we take measurements. We will be within the scale, right? We won't be off the scale. If we set our wavelength way over here, we pretty much only have about that much absorbance value possible for our samples, which means probably most of them will be off of the scale. The wavelength of light that we set our, say, the spectrometer to for absorbance values is the complementary wavelength to the color that we actually see. So if we look at a solution and it is red, we do not set our absorbance value to red's wavelength. We set it to our complementary color to red. So again, you would never really set the spectrometer to the color that you see because the light that's being absorbed is always complementary to that. Any questions on that there? But I think you have this guy worked out for you, so we'll kind of go through the calculations and see how we get there. So first off, if we take the absorbance maximum for this complex ion here, which has a coordination number of 6, is 470 nanometers. What is the color of the complex ion? So that is what I was just referring to. If the maximum wavelength is at 470, which would be like in this ballpark here, the color that the solution that we actually see would be its complementary color across the wheel there, and it would actually look orange to us. If we had a red solution, we would be setting our wavelength in that sort of greenish area, which is sort of what we did on that equilibrium experiment way back when. That's probably about in the range where your wavelength would have been. So to calculate the crystal field splitting, we basically have the wavelength given to us. So we really could use the energy equation that involves wavelength. And that's because both of those guys are constant. So right here is Planck's constant. That is the speed of light. And this is our wavelength that has been converted into meters. We cannot leave it in nanometers, otherwise we will be off by a factor. So that is where the 10 to the minus 9 comes from. In this particular case, that is a conversion between meters and nanometers. And that means that there are 10 to the minus 9 meters in 1 nanometer, by the way, is what that means. So in 1 nanometer, there are 10 to the minus 9 meters, is basically what that means. So doing that allows the units to properly cancel. That's because the speed of light's in meters, so those cancel, the seconds cancel. That leaves us joules, which is our crystal field splitting, and that's really joules per atom. So we could use Avogadro's number to figure out the energy per mole, and that's what we have here. That is Avogadro's number to basically convert into the energy per mole. That's how the atoms cancel each other out, basically. So those two guys cancel, leaves us basically joules per mole, and then we can divide by 1,000 to get kilojoules per mole. Any questions on that there? Yeah. So let's talk a little bit more about, how can we determine whether or not, the splitting between the d orbitals is going to be too large for the electrons to go up, or maybe not too large for it to go up. There's what's known as the spectrochemical series, and these are a bunch of ligands here. So we have I minus, Br minus, and on the other end, Cn minus, Co. And the guys to the left here are what are referred to as weak field ligands. That means that if you have any of those ligands present, what will happen is the split between the lower d orbitals and the higher d orbitals will not be very large. So that kind of delta will be small. And what that means is when electrons do sort of populate these d orbitals, they will go in like normal. So they will go in one at a time, and then eventually, if necessary, come back and sort of fill up. Now, if you have any of these sort of ligands on the sort of strong field side, What that means is when we have those d orbitals, we will get a pretty big split there in terms of the energy of the lower d orbitals and the higher d orbitals. And what happens in that particular case is the electrons will start to fill and decide, no, thank you, I don't want to go that high. I will go this way first until they really run out of options, and then they would have to kind of come up to the top. So the result of this is you're going to get a couple of things that's going to occur and a couple of descriptions that will occur. When we look at the differences in our electrons in each of these situations, the one that has more unpaired electrons is the guy on the left. And unpaired electrons are paramagnetic, right? They have their own electrical field, but they're unpaired. This is what is sometimes referred to as creating a high spin complex. So based on how those orbitals split, you will end up with a lot more unpaired electrons in this case, because they will go in basically one at a time. On the other end here, we have less unpaired electrons. And less unpaired electrons will result in what is sometimes referred to as a low spin complex. And a low spin complex means you actually have more paired electrons than unpaired electrons. So sometimes in problems, they'll say, draw the diagram for the high spin complex or draw the diagram for the low spin complex. And basically that relates to, you know, the splitting of those orbitals in terms of the energy difference. Now you may be asking, what about sort of the guys in the middle or water or something like that? And in that case, a lot of times they will sort of give you some direction. Like I said, they may say in the problem, draw the high spin, draw the low spin, you know, consider it a weak field or a strong field. So they'll give you some information as to how to approach it. If they don't give you information, it may actually not make a difference regardless. And that could also be the case. So for example, let's just say we had both our weak field and a strong field split that's happening here. So we'll just draw it like this. So this would be our strong field and our weak field. And let's just say that, you know, we had a d orbitals or electrons of only 3 electrons. In this particular case, if I did 3 electrons for my weak field, I'm going to end up like this. And if I did my 3 electrons for my strong field, I'm going to end up like that. And this guy on the left has 3 electrons, unpaired electrons. This guy on the right has 3 unpaired electrons. So sometimes it actually will not make a difference which one you do. And sometimes they will not give you directions on some of those because it really doesn't matter which way you do it. You will come up the same. A very common question, if you maybe can't get the idea of this, what we're talking about here is how many unpaired electrons are there? So that's a very common sort of question on these things is, you know, how many unpaired electrons would you expect to have in this complex ion? Any questions on that there? All right, so let's take a look at one here. For example, let's do this Fe. Actually, we'll do the nickel here. So we'll do the nickel Br6 2- here and take a look at it first. All right, so first off, we want to think about a couple of things. We want to think about what is the oxidation number there of our nickel. We should know that Br is Br-, so that is -1. There are 6 of them, which makes it -6. Has an overall charge here of the complex ion of -2. That means the nickel in this case is rolling with a +4 charge in this case. That's really important because we do want to know how many electrons we need to distribute in this guy. So if we went to nickel with no charge, so neutral nickel off the periodic table, that is number 28, which means we would have 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d8. Again, you could also shorthand it as we talked about earlier. That right there should be argon. 4s2, 3d8. So that would be the electron configuration for our nickel with no charge. Our nickel with a +4 charge would have 24 electrons, as it lost 4 electrons. As we talked about, when transition metals like nickel loses electrons, they come out of which one first? They always come out of the s electrons first. So we would lose 2 electrons out of the s. We then would still need to actually lose 2 electrons out of the d. And the electron configuration for this guy would be argon 3d6. Any questions on that there? So the d electrons that we're talking about in this complex ion are going to come from the nickel. And basically, we need to distribute 6 of these d electrons. Now, in this particular case, we are going to see that the coordination number here is 6, which means this is going to give us octahedral splitting, our geometry. And that's going to be this splitting right here. So we're going to get the 3 d orbitals on the bottom. We're going to get the 2 d orbitals there up on top. So we'll have our d orbitals, and we will have our 3 other d orbitals there, whoops, on the bottom. So x, y, y, z. What we got there? Zx. And all of our square guys there up on top, which would be x squared, y squared. And we have, what we got there, z squared. All right, so this would be the splitting that will basically occur here in this particular case. XC. Come on, it looked funny to me. All right, I'm gonna fix that. All right. So the other important thing is we want to also look at the ligand that is attached here. In this particular case, our ligand is Br. So we want to know, is that Br a sort of weak field, strong field sort of guy? And we do see that Br over here is at weak field. So what we know is this splitting is going to be weak field because of the ligand that's there. And what that means is the splitting that we see here is going to be relatively small because it's weak field. So we're going to distribute our 6 electrons like this. It would go 1, 2, 3, 4, 5, and 6 in this case. This would give us a total of 4 unpaired electrons, obviously here. This would be considered also a high spin complex in this case because we have a lot of unpaired electrons. Any questions on that there? All right, so why don't you try this one and this one here. So draw the splitting that occurs and determine how many unpaired electrons you would have in each case. So how many unpaired electrons, and also draw the splitting there. what we're dealing with in terms of charge, coordination number, and all those good things. So in this case, in terms of coordination number, it is going to be 6. Once again, there are 3 of these ethyl endyl diamines. That is the guy that we saw the other day that looks like this if you draw it. And it is a bidentate guy where both of those nitrogens per one molecule combined in. So that does give us coordination number of 6. Why that's important is the splitting that we are currently looking at is the octahedral coordination number of 6, sort of splitting of the d orbitals. We'll see in just a second that if it's a different sort of coordination number or geometry, there's some different splitting that sort of occurs of these d orbitals. Secondly, we also want to figure out the charge we got going on the nickel. So that is a 0 for our ethyl endyl diamine, which means our nickel here will once again have the +4 in this situation. It won't always be +4, but it happens to be. So we could also, again, steal really our electron configuration like we did earlier. So again, in this situation, we are going to have 6d electrons to distribute. We then want to look at our ligand and determine is it weak field or strong field. And again, if we look back on the, not that way. Again, go that way. We do see En is leaning towards strong, so we will do it as strong field in this case, which means when we go 1, 2, 3, it's going to decide that this is a little bit too far of a distance. So it would rather pair up in this case, and this would give us 0 unpaired electrons. Any questions on that one there? This obviously would then be a low spin complex, as obviously we have a lot of paired spin. That's what that means, right? Paired spin, quantum number of ms, right? Plus a half, minus a half. They're paired with each other. Any questions on that one there? All right, if we take a look at this guy here, we got our FeCN6 3-. Once again here, this is going to give us a coordination number of 6, as CN is monodentate, so there's 6 of them. That once again tells us we are doing the right splitting sort of arrangement over here. Our oxidation state there on the iron, CN is -1, and there's 6 of them, which would be -6. And there's a -3 overall, so it is going to be a +3 situation here for iron in this case. Iron with no charge has an electron configuration of argon 4s2 3d6. In this particular case, with a +3 charge, we will get rid of those, and we will also get rid of one of those guys there. That will leave us argon 3d5. So in this particular case, we're going to have 5d electrons to basically distribute. And once again, I'm going to steal the same graph here. So we'll steal this graph. Okay, then the last thing we probably want to determine once again is our CN- and sort of its relationship there. So CN- is again to the right there of En, so we'll do strong field once again on this. So this would be strong field. So as we start to 2, 3, once again going to decide those upper ones are too high in energy, so much rather pair off in this case. And we do actually end up with 1 unpaired electron in this particular case. Also would probably be considered low spin as well, since it only has 1 unpaired electron as well. Again, mostly you will get a lot of low spin complexes from strong field, as the separation is too large for them to kind of go up and kind of go one at a time. So that encourages sort of pairing up of the electrons, as opposed to weak field, which encourages them to kind of go in basically one at a time. And that sort of encourages unpaired electrons to basically happen and higher spin sort of complexes. Any questions on that there? So here's a couple of examples of iron 3, and again, this is the one we just did there, which is our +3, and this guy also is +3 here. And this is with fluorine, which would be on the other side, which is a weak field splitting here. So that's weak field. So the distribution again of those 5 electrons from the iron gets us a lot of unpaired electrons and a much higher spin than our low spin complex that we just did there. So here's all your sort of arrangements that you could get for high spin, low spin. And again, we see definitely with the stronger field, a more encouragement of everybody pairing up, as opposed to with our weaker field, which would be on that side, more of unpaired electrons. So again, what we are looking at is specifically for octahedral complexes, typically with coordination number of 6. Let's take a look at what happens when we get into tetrahedral complexes. Tetrahedral complexes would be a coordination number of 4 in this case. We get basically the same sort of splitting, except that it's reversed. So we have kind of our squared guys on the bottom and our kind of individual X, Y, and YZ there up on top. Works the same way. If we had a weak field, we would expect the electrons really again just to roll through and start populating before they come back and again sort of pair off. We obviously would calculate the number of electrons there was in the transition metal that's in the complex ion. And if we had a stronger field, we would then actually see the pairing off first before it decides to sort of come up there and kind of fill up the top ones. So again, really works the same way as sort of the flip of octahedral splitting, this tetrahedral arrangement. Any questions on that one there? Now, also with the coordination number 4, you could get the square planar, 4, which is that sort of exception to the octet rule, but we do get a lot of crazy splitting happening here. So we get some of our XYs and our squared guys up on top and bottom and a bunch of splitting. It does still work the same way. Again, electrons will always feel lowest to highest in terms of the splitting that occurs. For us, we will not worry about square planar splitting, but you are responsible for tetrahedral and octahedral splitting. So you're responsible to know those two. We will leave the crazy square planar out of it as well.